Okay, so this is the first lesson of our A2 Pure Maths course, and it follows on from the two web lessons 23 and 24 that you did over the summer holidays, and they were on the chain rule as well. So it's really just consolidating and extending that work a little bit. Okay, so let's get cracking. First question. So it's asking us to differentiate this, and we can apply the chain rule because the condition is you have to have a set of brackets, which we've got, and all of the x's have to be inside the brackets, and they are. All of our x's are inside the brackets. So, and we're going to do it by sight, which is the method that you learnt in the web lesson in the actual animation. And so really what we're going to do is we're going to say dy by dx is going to be, now here I've got brackets to the power 6, so it's very much like differentiating x to the power 6. When you differentiate that, you get 6x to the 5. So the same thing here, the 6 is going to come down, you're going to get 1 minus x squared to the power 5. But I've left a little gap here, and the little gap I've left in there is for the extra step for the chain rule. The extra step for the chain rule is to multiply by the differential of the brackets. So the inside of the brackets, 1 minus x squared, if you differentiate that, it'll give you minus 2x. And so 6 times minus 2 is minus 12. X brackets 1 minus x squared to the power 5 is our dy by dx. Okay, and again we can easily check that. We can do 1.2 store as x, and then we can type in this equation, and that will give us the gradient on this curve at 1.2. But our calculator has its own way of finding the gradient, so we could just type in this equation into the d by dx button of the calculator and put 1.2 in the box at the end and see if it gives the same answer. So every single one of these questions we can easily check them. Okay, so I'm going to rewrite this using indices first. So y equals 3x squared minus 1 to the minus 1. And then now I'm going to differentiate it. Dy by dx equals, the minus 1 is going to come down. Then it's going to be 3x squared minus 1 to the minus 2. So bring down the power, knock 1 off the power. Extra step, multiply by the differential of the brackets, which is 6x. Now as you get used to this, you'll be able to do all of it in one go. 3x squared minus 1 squared, and I've just gone back to from indices notation back into a fraction, back into symbol notation. Again, rewrite it using indices. 1 plus x squared to the power a half. And then now I'm ready to differentiate it. So I'm going to try and do it in one go now. The half is going to come down. It's going to give me 1 plus x squared to the minus a half here. And the half is going to multiply by the differential of these brackets. And the differential of those brackets is 2x. So a half times the 2x is just going to give me x. And so the answer is x over square root 1 plus x squared. Again, I've gone back from indices into symbol notation using the square root symbol. Dy by dx equals 5 x squared minus x to the power 4, and then multiply by the differential of the brackets. The differential of brackets is 2x minus 1. I'm going to have to put that in brackets because there's two terms in that differential. I have to put that in brackets. If you don't write the brackets in, then you'll end up getting it wrong. And there's no point in multiplying that out. Just leave it factorised. It's much nicer left factorised like that. Okay, we can't use the chain rule here. The rule is all the x's have to be inside the set of brackets. So all the x's aren't inside the set of brackets. So maybe we'd have to multiply that all out, and that would be one way of doing it, simple polynomial differentiation after a huge expansion. Or there is a different rule which we're going to learn next week, which is the product rule, which is how to deal with one term which has got x in two places and there's a multiply by somewhere between those two. Okay, so for this one we're just going to write not applicable. So chain rule is not applicable. So we're just going to write NA, not applicable. And with this homework, if you get a question which can't be answered using the chain rule or by simple polynomial differentiation, then you just say not applicable. Okay, so dy by dx is going to be 3x plus 1 over x to the power 2. And I need to multiply by the differential of the brackets. Differential of the x is going to be 1. Differential of 1 over x, well remember that's x to the minus 1. So when you differentiate it, x x to the minus 1. When you differentiate, it gives you minus x to the minus 2, minus 1 over x squared. There's my answer. Next one, rewrite it using indices, x squared minus 2 to the minus 3. And then differentiate it. All my x's are inside the bracket, so I can use the chain rule. The minus 3 is going to come out. It's going to multiply by the differential of that. It's going to give me minus 6x brackets x squared minus 2 to the minus 4. And that gives me minus 6x over x squared minus 2 to the power 4. So here I'm going to, well, first thing I'm going to do is I'm going to distribute the square root. So like if you have square root of a over b, you can write that as square root of a over square root of b. So I'm going to do that here. I'm going to write that as square root of 4, which is 2, over square root of x squared minus 2, which gives me 2 x squared minus 2 to the minus a half. So that's my y equals. Now I want to differentiate it. So dy by dx equals, the minus a half is going to come down and multiply the 2, which is going to give me minus 1. Then I'm going to get the differential of the x squared, which is 2x, and x squared minus 2 to the minus 3 over 2, which is minus 2x over x squared minus 2 square rooted and cubed. Next question. Okay, so again I'm going to rewrite this using indices, so that's going to be 5, 2 minus x to the minus a half to the power minus 3. And now I'm ready to differentiate it. Dy by dx equals, so the minus 3 is going to come and multiply the 5, so that gives me minus 15. And then I'm going to multiply that by the differential of these brackets. And the differential of the brackets is going to be minus 1 times minus a half. So a half x to the minus 3 over 2. So that's going to give me minus 15 times a half x to the minus 3 over 2, and then 2 minus x to the minus a half to the minus 4. And then just tidy that up. I'll write that as a big fraction. The 15 is going to go on the top of the fraction. The minus can stay on the top of the fraction. The 2 is going to go on the bottom. This x to the minus 3 over 2, if I push it down to the bottom, it's going to become x to the 3 over 2, which is x cubed and then square rooted. And then this is going to become 2 minus 1 over root x to the power minus 4. So I've pushed it down to the bottom, so that will become to the power 4. And so there's my dy by dx. Again, we can easily check that. So that's 2, 1 plus 3x to the power minus a half. And so my dy by dx is going to be, the minus half will come down and multiply by the 2. So that's going to be minus 1. And then I have to multiply by the differential of the brackets. Minus 3, 1 plus 3x to the minus 3 over 2, which gives me minus 3 over 1 plus 3x cubed and square rooted. Next question is, just rewrite it using indices. Minus 2, 1 minus 2x to the half to the power minus 2. And then differentiate it. Dy by dx is going to be, the minus 2 comes down and multiplies the minus 2. So if you think, oh, I might make a mistake, you can do it more slowly. So you can do minus 2 times minus 2 is 4, leave a space, 1 minus 2x to the half to the power minus 3. And then I need to multiply by the differential of the bracket. So the differential of this bracket is going to be, well, the 1's going to disappear. That's going to give me minus 2 times a half, so minus 1 x to the minus 3 over 2. So minus 1 x to the minus 3 over 2. And again, we can tidy that up. We can write that as minus 4 over x cubed square rooted 1 minus 2 root x to the power 3. So that's going to be 3 1 minus x squared to the power a third minus a third. So I have to push that up. And so dy by dx is going to be the minus a third times a 3 gives me minus 1 times the minus 2x, which is the differential of that, gives me 2x brackets 1 minus x squared to the knock 1 off the power minus 4 over 3, which gives me 2x over 1 minus x squared to the power 4 cube rooted. Okay, you've got a set of brackets, but you haven't got all the x's inside the set of brackets. So this wouldn't be the chain rule. Later on we will learn to do that using the product rule. Okay, you've got a set of brackets here, but all your x's aren't inside that set of brackets, and then you've got another set of brackets here, and all your x's aren't inside that set of brackets either. So it's not strictly speaking the chain rule, but this would be an easy one to remedy. So y equals, just multiply out that denominator, so it gives me x squared minus x minus 2, and then rewrite that as x squared minus x minus 2 to the minus 1. And then now we're ready to differentiate it. dy by dx equals, the minus 1 comes down, x squared minus x minus 2 to the minus 2, multiplied by the differential of brackets. That's going to be 2x minus 1, 2x minus 1. And then just tidy that up. It's going to be minus brackets 2x minus 1 over. This one's going to go down to the bottom of the fraction. But remember, this thing here is just really that. So I can refactorize it. So I can call it x plus 1, x minus 2. But it's to the power 2. I mean, the minus I've already done by pushing it down. But it's still to the power 2. So I'll square them both. And then one last simplification. We talked about this last year. Minus brackets a minus b. It'd just become b minus a. So here again, that minus brackets 2x minus 1 would just become 1 minus 2x. Okay, so let's rewrite that. Y equals 1 plus x squared minus 1 to the power half to the power 4. Now all of our x's are inside a set of brackets, so it is the chain rule. But that set of brackets is inside another set of brackets. So it's actually a double chain rule situation. And when we see those, we go back to first principles. So first principles, look at the big set of brackets. Everything inside that big set of brackets is going to be replaced with u. So it's going to be y equals u to the 4 and u equals 1 plus x squared minus 1 to the power half. And then we differentiate this, dy by du equals 4u cubed, du by dx equals, and we're using the chain rule here because it is a double chain rule situation, so we're using the chain rule here, but this chain rule we can just do by sight. We don't need to go to first principles for that. So the half is going to come down, it's going to multiply by the 2x, it's going to be x squared minus 1 to the minus a half. And then we just multiply these two together, so we just multiply that and that together, and we get 4x brackets x squared minus 1 to the minus a half times u cubed. I always put the u at the end because it's just easier, then I know I've got to replace it. So I've got to replace that u with this. So that u's got to be replaced with this. And so that gives me dy by dx equals 4x brackets x squared minus 1 to the minus a half times 1 plus x squared minus 1 to the half, all cubed. Okay, I'll just tidy that up a little bit. So that's going to give me 4x 1 plus root of x squared minus 1 all cubed all over x squared minus 1 square rooted. Okay, so let's just tidy it up a little bit. Again, you have a situation, I can see already, even though it's not written out fully yet, it's going to be a double application of the chain rule. So y equals 2 minus x cubed to the power 4 all to the power half. So all of your x's are inside a set of brackets, but that's inside a second set of brackets. So take the bigger set of brackets, replace everything inside that bigger set of brackets with u. So y equals u to the half and u equals 2 minus brackets 2 minus x cubed to the power 4. Okay, so differentiate this. dy by du equals a half u to the minus a half. Differentiate this, du by dx equals, the 2 is just going to disappear. Here we're going to get the 4, it's going to multiply by the minus 3x squared, it's going to be minus 12x squared 2 minus x cubed to the power 3. And then multiply these two together. Multiply that and that together and call it dy by dx. So dy by dx is going to be a half times minus 12, which is minus 6 x squared 2 minus x cubed to the power 3 times u to the minus a half, and then I'm going to stick back in what u stood for, which is this. So minus 6x squared brackets 2 minus x cubed to the power 3, and then it's u to the minus a half, so it's over square root of u, and u was 2 minus x cubed, whoops, brackets 2 minus x cubed to the power 3. Okay, so there's my answer. Okay, one of the reasons that we want to be able to do the chain rule by sight and not revert to first principles is because it will allow us a much better understanding when we need to integrate. Differentiation is easy, it's algorithmic, so as long as you follow the rules you'll be able to differentiate. It might seem difficult when you're first doing it, but it will get easier and easier and easier, and by the time you're sitting your exam you'll be saying differentiation is easy. But integration is always a little bit more tricky, and it will remain a little bit more tricky even after you've finished learning it and even as you're getting ready for the exams. So this technique, reverse differentiation, is going to be an important technique for us to integrate things. So the first thing it's asking us to do is to differentiate that, and that's just the chain rule. We can do it by sight, it's not a particularly difficult one. So I'm going to differentiate that by sight, and I'm going to just differentiate that, and I'm going to write that the 4 is going to come down, it's going to multiply by the 3x squared, so it's going to be 12x squared x cubed minus 3 to the power 3. So there's my differential. Now they're asking me to integrate this. Oh, what a coincidence. The thing that they're asking me to integrate is identical to the answer that I got when I differentiated this. When I differentiated this, this was the answer I got. And that's identical to the thing that they're asking me to integrate. And we know that integration is the reverse of differentiation. So basically all I'm going to do is take that arrow and point it the other way. And I'm going to say, right, if you're integrating, if you start with this and you integrate, go in the opposite direction, you'll get back to this. So the answer is just x cubed minus 3 to the power 4. And it's just using the property that if you differentiate that, it gives you that. Therefore, if you integrate that, it will take you back to there. Okay, so now this statement that we have here, it's a statement that we can modify. We can multiply both sides of it by any number, any constant. So by 2, by 5, by root 3 if you want to, by pi if you want to, by minus a half if you want to, but nothing containing x in it. So now they want me to integrate this. Now already I know how to integrate this. So when they're asking me to integrate this, I'm thinking, well, it's kind of similar to the one they just asked me to integrate. In fact, instead of a 12 at the front, it's got a 6 at the front. That's the only real difference. Instead of a 12 at the front, it's got a 6 at the front. So I'm thinking, why don't I halve both sides of this? Why don't I times both sides by a half? So times a half times a half. This would then become 6x squared x cubed minus 3 to the power 3, and it would integrate to give me a half x cubed minus 3 to the power 4. And so there's my answer, a half x cubed minus 3 to the power 4. Now both of these need a plus c on them, of course, but the technique is to use differentiation to help us to integrate. So that's what's happening here. We're trying to integrate something, and the differentiation is helping us to do that integration. Okay, so the last question is, well, it's the same again, but this time it doesn't even have the 6 in front of it. So what I'll do is go back to the original statement, and this time I won't times it by a half because that will make it 6. I'm going to times it by a 12th. So if I times it by 1/12, then that's just going to become a 1x squared, and I times this by a 12th, and that's going to become a 12th brackets x cubed minus 3 to the power 4 plus c. Okay, so again they're asking us to differentiate something, so we're going to start off by differentiating that. So that's going to give us the 3 over 2 is going to multiply the minus 2x, which is a differential of that. So that's going to give me minus 3x brackets 1 minus x squared to the power a half. Now, the thing that they've asked me to integrate is, they've asked me to integrate x brackets 1 minus x squared to the power of half. Now that's not exactly the same as this, but it's pretty damn similar. So what I'm going to do is, well, the only difference is this minus 3. So I'm going to times both sides of this equation, of this this rule that I've worked out. I'm going to times both sides by minus a third. So times minus a third times minus a third. And I'm going to reverse the error. I'm not going to look at differentiating, because I'm not starting from this side and differentiating and going to, I'm starting from this side and integrating and going to the other side. So that gives me x 1 minus x squared to the power of half integrates to give me minus a third 1 minus x squared to the power 3 over 2. So the answer is minus a third 1 minus x squared to the power 3 over 2 plus c is my answer. Okay, and I'm going to show these 3 lines of working when I do these. Okay, so if you think about it, what happened on the last 2 questions is we were ultimately trying to find an integral, but they told us what to differentiate to start off with to help us. So that's sort of cheating, isn't it? They're sort of giving us 80% of the answer already. They're saying, well, why don't you start with this? Now we're up to just straightforward, pure integration. Find this integral. And we want to use the same method as we did in the last one. And the last one, what we did was he started by differentiating something where when we got this answer, it was kind of similar to the thing that we wanted to integrate. So the rule here is going to be really simple. We're going to start off by differentiating something. And the thing that we're differentiating, I'm going to call it a guess. You'll see why I'm going to call it a guess later on. And it's basically going to be copying the whatever is inside that set of brackets. So it's that whole of that set of brackets, but with the power raised by 1. So not 7, but 8. So, and I'm ignoring the 4, completely ignoring the 4. So that gives me 1 minus 2x to the power 8. When you differentiate that, it's going to give you the 8's going to come down, it's going to multiply by the minus 2, it's going to give you minus 16, 1 minus 2x to the power 7. Now, I started from here and I differentiated. If you start from here and you integrate, well then you get to this answer here. So I'm just going to rewrite that arrow in the opposite direction to just remember that integration is the reverse of differentiation. Okay, so I found an integral. I figured out how to integrate this. But that doesn't match exactly what I was supposed to be integrating. But it's quite easy to fix because I want to change that minus 16, I want to change it to a 4. So I'm going to divide it by 4. Oh, but hold on, I've got to change the sign as well. So I'm going to divide it by minus 4. So I'm going to times it by minus a quarter. So times by minus a quarter, times by minus a quarter. And so that's going to give me 4, 1 minus 2x to the power 7, integrates to give me minus a quarter, 1 minus 2x to the power 8 plus c. So there's my answer. My answer's strangely on the left hand side, so make sure that whoever's marking it can see where your answer is. Yeah, they might expect your answer to be here on the right hand side where your answer normally is. So again, we copy the set of brackets, ignore the 3, and just up that power by 1. So 2x plus 1 to the power 6. Differentiate that, and hopefully it will give us something that's quite like that. So differentiate that. The 6 comes down, multiplies by the 2, 12, brackets 2x plus 1 to the power 5. Now that doesn't exactly match what we're supposed to be integrating, but it's quite an easy fix from there. So first thing is, let's reverse this arrow to say, okay, so if you didn't start from here and differentiate to get to here, you could go the other way. You could start from here and you could integrate, and that would take you back to this answer here. Okay, so I don't want 12. I don't want to integrate 12 to x plus 1 to 5. I want to integrate 3 to x plus 1 to 5. So I'm just going to times both sides by a quarter. And so it's going to be 3 brackets 2x plus 1 to the power 5 integrates to give me a quarter brackets 2x plus 1 to the power 6 plus c. I'm going to rewrite this using indices. 2 brackets 4 minus 5x to the power minus 2. And I'm going to guess just by adding 1 to the power bracket. So use exactly the same set of brackets. 4 minus 5x, ignoring anything in front of the brackets, and add 1 to the power. Now I'm going to differentiate that. And so it's going to be minus 1 times minus 5, which is 5, brackets 4 minus 5x to the minus 2. And it doesn't match that exactly. So what do I need to multiply it by? Well, if you're not sure, it's always the one you want, the number you want, 2, divided by the number you've got. So times 2 over 5, times 2 over 5. And change that arrow to integration, because we're going in the opposite direction. So it's going to be 2, 4 minus 5x to the minus 2, integrates to give me 2/5 brackets 4 minus 5x to the minus 1 plus c. That probably needs a bit of tidying up. Let's call that 2 over 5 brackets 4 minus 5x plus c. Okay, that's quite complicated. That looks like a pretty tricky integral. But the method that we're going to use, which is reverse differentiation or recognition, will actually make this look quite easy. Rewrite it using indices first of all. 2x, 4 minus x squared to the power minus a half. My guess is I'm going to ignore that. I'm just going to look at these brackets, and I'm going to use the 4 minus x squared, but I'm going to add 1 to that power. So 4 minus x squared to the power a half is going to be my guess. When I differentiate that, half's going to come down, it's going to multiply by the minus 2x. So it's going to be minus x brackets 4 minus x squared to the minus 3 over 2. And then it kind of matches what I'm supposed to be integrating. Doesn't match exactly, but it kind of matches. I just need to multiply both sides by minus 2. Now I'm going to abbreviate my working. I don't want you to, for your homework, I want you to keep it to the full 3 lines of working. But I'm just trying to explain to you that later on, as we get familiar with this, we will abbreviate this to 1 line of working and then eventually to no lines of working and just write the answer down. That's perfectly acceptable to do that. Okay, so I'm going to multiply both sides by minus 2. So if I multiply this by minus 2, that's going to become a 2. And that's going to become a minus 2. And there's my answer. It just needs a plus c on it. Okay. Right. Go back to the chain rule, and this time we're looking at non-polynomials. Again, we did this in the second web lesson, and this is just reminding us of that work and just extending it a little bit. The rules we learned were that sine x differentiates to give us cos x, and cos x differentiates to give us minus sine x, and tan x differentiates to give us sec squared x. And those are our 3 new rules. Although in reality, almost always we will have some brackets and some stuff inside those brackets, and we'll have to use the chain rule. So in this case, we don't really, I mean, you can put a bracket around the x there, but you don't really need to if you don't want to. So all we're doing is using this rule here, which is differential of sine x is cos x. So differentiate sine x is cos x. The 2 is just going to stay there. It's not going to be affected. So 2 cos x is our dy by dx, if that's y equals. Differentiate sine 2 theta. So you see what I mean? We've now got brackets here and we've got stuff inside the brackets. So that means the chain rule. So now we're going to do it by sight. We're not going to do it by first principles. So we know that when you differentiate sine of something, you get cos of the same thing. So cos 2 theta. But remember, the extra step for the chain rule is you have to multiply by the differential of the brackets. And differential of that is just going to be 2. So there's our answer. Next question. We're differentiating. Okay, so if we differentiate cos of something, we're going to get minus sine of the same thing, 2x minus pi over 2. There was a half in front of this, and that half is kind of going to just stay there as well. Oh, but remember, we've got to multiply by the differential of the brackets. That's the extra step for the chain rule. So multiplying by the differential of the brackets, differential of the brackets would just be 2. So if I multiply that by 2, then I'm going to get 2 over 2, which is just 1. So I could just ignore that, and it's minus sine, brackets 2x minus pi over 2. Let's rewrite it using indices. So that gives us sine x to the power minus a half. Now you've got to watch out. This question trips up some students. And the reason is they know that when you differentiate sine of something, it changes to cos of the same thing, and you've got to multiply by the differential of the brackets. But look here. Look for the brackets. Whenever you're using the chain rule, there should be brackets. Look for those brackets. Here are the brackets. Once you've found the brackets, look to see what is outside of the brackets. What is outside of the brackets is a power of minus a half in this case. So you have to differentiate it like you differentiate a power. What do I mean like you differentiate power? Like you differentiate x squared plus 3 to the power 4. The 4 comes down, you knock one off the power, you multiply by the differential of the brackets. So the same thing happens here. Is going to be the minus a half is going to come down. You're going to sine x to the minus 3 over 2, and you're going to multiply by the differential of the brackets. Differential of sine x is cos x. And just tidy that up. Let's write a fraction. Let's write the minus cos x on the top, and let's write the 2 on the bottom, and let's write this sine cubed x square rooted on the bottom as well there. So we know when you differentiate tan of something, it gives you sec squared of the same thing. But you have to multiply by differential of the brackets. That's the extra step for the chain rule. Differential of the brackets would be minus a half. Okay. If you want to check this, you can. You can check it on your calculator. Type in 1.2 store as x. Type in that equation. That will give you the gradient at 1.2. Then use the d by dx button on the calculator to get the gradient at 1.2 using the original equation, using the calculator's method of differentiating. Now you have to watch out, because differentiation and integration only works in radians mode. So if you're calculating in degrees mode, it's not going to work. You've got to be in radians mode for you to get the right answer. Okay, next question. Okay, if you wanted to put some brackets, maybe you could put them there. That's the only place I can think of to put any brackets. Well, all my x's aren't inside a set of brackets, so this is not the chain rule. So this is actually the product rule, but we're not doing those, so we just say not applicable. Chain rule is not applicable to this. My next question, tan squared 5x. Okay, I'm going to write this out because the way that's written there misses out a set of the brackets. It's the same as tan of 5x squared. So what you can see is there is a set of brackets, and all your x's are inside that set of brackets, but that's inside another set of brackets. That's a double helping of the chain rule. So we need to go back to first principles. So I'm going to write it as y equals, replace the thing inside the big brackets with u. Y equals u squared, u equals tan of 5x. Differentiate that, dy by du equals 2u, du by dx equals, so when you differentiate tan 5x, you get sec squared 5x. And you have to multiply by the differential brackets, which is 5. Multiply the two together and call it dy by dx. dy by dx equals 2 times 5 is 10. Sec squared 5x times u. Yeah, but u was tan of 5x. So I'll just replace the u with tan of 5x. Times tan of 5x. Okay, so there's our answer. Now I'm just going to tidy that up. I want to get rid of some of this working here. I just want to write that answer in there. So if we differentiate this, it gives us 10, and maybe I'll put the tan 5x on the front. Tan 5x, because it doesn't have a power on it, whereas the sec squared does. Sec squared 5x. Okay, I'll just get rid of that working now. We've done that. Okay, and now they're asking us to integrate this, and well, that looks a lot like that. And we know how to integrate that already, because if you differentiate this, you get this. So that means if you integrate this, you'll get that. So we're looking at it the other way around. So let's just rub that arrow out, change it to point the other way, and say if you integrate 10 tan 5x sec squared 5x, it will take you back to tan squared 5x. We want to integrate this, which doesn't have the 10 in front of it, so times a tenth times a tenth. And so the answer is going to be a tenth tan squared 5x plus c. So we're doing differentiation at the moment, but I'm introducing you to these integrals because integration is going to be more difficult, and I want to get you going on it a bit early. So it's asked me to differentiate this, so I'll just rewrite it as 1 plus sine theta squared. We know that that's what sine squared theta means, all to the power of half. And again, it's a double helping of the chain rule. So replace everything inside the big brackets with u. Y equals u to the half, u equals 1 plus sine theta squared. Differentiate this, dy by du equals a half u to the minus half. Differentiate this, du by d theta equals, so the one's going to disappear. This, you've got to treat it like a polynomial, because outside of, look for the brackets. Brackets are here. What do you see outside of brackets? You see a power 2. So bring the power down, knock one off the power, multiply by the differential of the brackets. So that's going to be 2 times sine theta times the differential of sine theta, which is cos theta. 2 sine theta cos theta. And then multiply the two together to get dy by d theta. dy by d theta is going to be half times 2, which is 1. Sine theta cos theta times u to the minus half times u to the minus, so at the bottom of the fraction, half square rooted. And then inside here is going to be u, but I know u is 1 plus sine squared theta, 1 plus sine squared theta. Differentiate sec theta, or sec x. Well, there's no brackets at the moment. Oh, but hold on, sec x is 1 over cos x. Let's rewrite it as 1 over cos x. And let's rewrite that as cos x to the power minus 1. Now, we've got to differentiate that. That is the chain rule, but if you look at where the brackets are here. Outside of the brackets is a power minus 1. So you've got to differentiate like a polynomial, like a power. So the minus 1 comes down and you knock 1 off the power. So that gives you dy by dx is going to be minus cos x to the minus 2. And then you've got to multiply by differential of the brackets. Differential of cos x is minus sine x. So minus times minus is going to be plus sine x. And then just tidy up. Sine x over cos x to the power minus 2 means you've got to push it down to the bottom of the fraction. So it's going to be cos squared x to the bottom of the fraction. I'm going to write it as cos x. And you're going to say, why do you write it as cos x, cos x? Well, because then I can say to you, well, what is this? Sine x over cos x. And you say, well, it's just tan x. And I'll say to you, what is this? And you say, well, what do you mean, what is that? There's nothing on the top of the fraction. All right, fine, I'll put a 1 there for you. Put a 1. What is that? 1 over cos x. So, well, that's sec x. That's what we started off with. Okay, so then the answer is tan x times sec x. So sec x tan x is our answer. Okay, so we've done that. Differentiated and simplified our answer. So we differentiated that. And the answer was sec x tan x. Now, effectively, what we've learned is a new rule. We can add that to, we had rule 2, rule 3, and rule 4, which were, differentiate sine x, you get cos x, differentiate cos x, you get minus sin x, differentiate tan x, you get sec squared x. This is a new one, so we can add this rule. Differentiate sec x, you get sec x tan x. And once we've learnt a new rule, we can just simply apply the chain rule to it. Even though it's new to us, we can just immediately start applying the chain rule to it. So they say differentiate sec 3x. So if you want to differentiate sec 3x, now somebody who doesn't know the chain rule might think that if you differentiate sec x and you get sec x tan x, then if you differentiate sec 3x, then of course you should get sec 3x tan 3x. And they'd be right to a point, but they've forgotten something. They've forgotten that you're now using the chain rule. There's now brackets, so you have to multiply by the differential of the brackets. So the differential of the brackets is just going to be 3. So there's our answer. Now it says differentiate sec a half x squared. Again, somebody who doesn't know the chain rule, but just has come across this rule here, which is that sec x differentiates to sec x tan x, they might think that the answer is sec a half x squared differentiates to sec a half x squared tan a half x squared. They'd be wrong, but they wouldn't be far wrong. They realise that if you replace that x with a half x squared, then you've got to replace those two x's with a half x squared. But they forgot that that means you're now applying the chain rule because you've got brackets, so you need to multiply by the differential of the brackets, and the differential of a half x squared is, well, it's just x. So there's the correct answer. Okay, now we want to differentiate logs. But before we can differentiate logs, we need to refresh our memory on how we expanded logs last year. So we learned all this last year, so just refreshing it for us. And these were our 3 rules for expanding logs. So if you see something like this, you can write it as ln 3 plus ln x. That's just using that rule. If you see this, you can write it as ln a half plus ln x to the power 4. That's just using that rule again. But now you can use this rule, which means you can bring that 4 down to the front there. So it's ln a half plus 4 ln x. Now, if you're paying attention, you'll also know that the ln a half could be rewritten as minus ln 2, because a half is 2 to the minus 1, so you could use that rule again. Next one, let's rewrite it using indices first. So that's ln. I'm going to write it as ln 4 over x to the power a half. I could have written it as 4x to the minus half, but I just couldn't be bothered to take the x up as well. I was feeling a bit tired. So now I can use this rule, which is for a fraction. So it's going to be ln 4 minus ln of x to the power a half. And so that's using this rule here. And now I can use this rule again, which is bringing that power down. So bringing that power down to there. And ln 4, well, 4 is 2 squared, so that's 2 ln 2. Maybe you'd rewrite that as well. Okay, so what I want to explain to you is these don't get any more difficult. You know, even when I get to here, they don't get difficult. And the reason is there's a simple way of dealing with them all. All the factors on the top of the fraction, so let's colour them in yellow. All the factors on the top of the fraction will all become positive logs. And all the ones on the bottom of the fraction, let's colour them green. they'll all become negative logs. So if I want to expand this, it's very simply going to be ln 4 plus ln x cubed. You're saying why plus? Because it's on the top of the fraction. Minus ln 2 minus x. You're saying why is it minus? Because it's on the bottom of the fraction. Minus ln 1 plus 2x all squared. Now this 3 can come down to the front, and this squared can come down to the front. And that's it, done. Ln 4 plus 3 ln x minus ln 2 minus x plus 2 ln 1 plus 2x. Easy. Okay, so we want to differentiate logs. So our next rule is when you differentiate ln of x, it gives you 1 over x. But that would only be the case if you weren't applying the chain rule. Here I don't need to apply the chain rule. In most situations you'll have some brackets and you have to apply the chain rule. So if I was differentiating ln of 2x minus 5, I might think the answer is 1 over 2x minus 5, because ln of something gives you 1 over the same thing. So ln of 2x minus 5 gives you 1 over 2x minus 5, but you have to remember to multiply by the differential of the brackets. Differential of the brackets is 2, so times it by 2. So there's my differential. Differentiate ln x, we know that's 1 over x. Differentiate ln 2x, well, we said you must expand the log before you differentiate it. So I'm going to write that as ln 2 plus ln x. Now I'm going to differentiate it. Ln 2 doesn't have any x's in it. It's just a number. You can stick it in the calculator. It's something like 0.693. When you differentiate a number like 0.693 or 5 or minus half, it disappears. So that ln 2 is going to disappear when you differentiate it, and all you've got left to differentiate is the ln x, which gives you 1 over x. Same here, you've got to expand it. Ln 5 plus ln x, then differentiate it, and the ln 5 is going to just disappear. Gives you 1 over x. Same here, differentiate, it's going to give you 1 over x. And then they ask, so what's the integral of 1 over x? Well, if differentiation and integration are the opposite of each other, then the integral of 1 over x could be that, or it could be that, or it could be that, or it could be that. And the difference between them is just this number in front of the x. So you might argue that the answer could be ln of kx. And you'd be right. I mean, you might say, oh, but hold on, surely the simplest answer is just ln x. It is. And then of course you have to put plus c. So the k takes the place of the plus c. So we've got two ways of writing it when we integrate 1 over x. We can write it as ln of kx or ln of x plus c. I'm going to actually change that a little bit more as well. I'm going to say we prefer this one. So we will prefer this rather than the plus c. I'll explain to you why later on. But I'm also going to change these brackets. I'm going to change these brackets to a modulus sign. And the reason I'm going to change those brackets to a modulus sign is because let's say I wanted to integrate the 1 over x graph and find the area between, say, minus 2 and minus 1. So I wanted to find that area. Obviously it's going to be a negative area because it's below the x-axis. I would type in integral between minus 2 and minus 1, point on the left, point on the right, of 1 over x dx. Now I know that that's ln kx. I don't need the constant because I'm doing a definite integral, so I'm just going to call it ln x. Now if I don't use the modulus, what happens is I try and type in the minus 1 and the minus 2, and you can't do ln of negative 1 and you can't do ln of negative 2. But if I put the modulus in there, it fixes that problem. So it allows us to find the area on the original graph. So you're just going to have to remember that that's the rule. We're going to use a modulus whenever we do those. Now it's asking us to differentiate that. So remember with logs, if you have ln a to the power n, that n can drop down in front of the log. So we're going to do that here, 2 ln 3 minus 2x, and then now we're ready to differentiate it. Let's ignore the 2 for a second. It's going to give you 1 over 3 minus 2x times the differential of the brackets, which is minus 2. Oh, but there was a 2 at the front, so minus 4 on the top. Okay, so one of the things about logs is because you can expand them so nicely, something that looks horrendous is actually quite easy to differentiate. So I'm going to expand this log. It's going to give me ln of x cubed plus ln of x squared minus 1 squared. Oh, and I can use the next rule for logs as well. I can bring that 3 down there and bring that 2 down there. Okay, so all I've done is expanded the log. Now I'm ready to differentiate it. So when I differentiate this one, you're differentiating ln x, it gives you 1 over x, but you've got a 3 in front of it, so it gives you 3 over x. Plus, differentiating this, it gives you 1 over x squared minus 1 times the differential of the brackets, which is 2x, but then there's a 2 here, so 4x. Differentiate log to the base 10 of x. Well, we don't know how to differentiate logs when the base isn't e, so we want lns all the time. We want the base to be e. Ln means log to the base e. So what are we going to do here? Well, remember I told you that my calculator doesn't have your calculator is this log box button, so you can type in log to the base 2 of 8 on your calculator and get the answer. I can't type that in on my calculator. I have a log button and a ln button, but not this button here. So how would I do it? Well, I would type in ln 8 divided by ln 2 and it would give me the same answer. And similarly, this could be written as ln x divided by ln 10. Now the ln 10 is just a number. You can stick it in your calculator and find out what it is. It is just 2.3, roughly 2.3025. So you can treat this as 1 over 2.3 times ln x. And that's not accurate, so it's a bit rubbish that I've done that. I should have just left it as ln 10, but never mind. Now I want to differentiate this. Differentiate the ln x, it gives you 1 over x. Oh, and I've got to multiply it by 1 over 2.3. So that gives me 1 over 2.3x. And that 2.3, well, that was ln 10, wasn't it? Let's just put it back. It's not accurate if I write it as 2.3. Put it back as ln 10. Then that's more accurate. And so there's our answer. So we can differentiate even if the base isn't e. Ln of sec of x, it gives you 1 over sec of x. Oh, but you have to multiply by the differential of the brackets. Now remember, we worked out the differential of sec x earlier on. It was sec x tan x. So we can put sec x tan x. Oh, the sec x's cancel out. So we just get tan x. Oh, that's a nice simple answer, isn't it? Wasn't expecting such a simple. That means we can integrate tan x now, because we differentiated that to get that. So we've already learned that the integral of tan x is ln of sec of x. Well, I need those modulus signs, don't I? Ln of sec of x. So we've learned an integral. Whenever you differentiate something and the answer comes out as something that you already recognize and know, and you didn't know that that was going to be the answer when you differentiate it, then you've learned a new integral. Okay, now we're on to differentiating exponentials, and we know that the differential of e to the x is e to the x, but that's not applying the chain rule. Almost all the time we'll have some brackets. We'll have to apply the chain rule. So if I differentiate this, it's going to give me, differentiate e to the 5x, it gives you e to the 5x. Oh, but you've got to multiply by a differential of the brackets, 5e to the 5x. Differentiate e to the x squared, it gives you e to the x squared. Oh, but you've got to multiply by a differential of the brackets, 2x e to the x squared. And now it's asking me to integrate this, which does look quite a bit like this. Instead of having the 2 there, you've got a 10 here. So I'm going to reverse my arrow. So I'll rub that arrow out, take it the other way so that I'm integrating. And then I'm going to say, yeah, but I want 10. So I'm going to multiply this by 5, so that's going to become 10. And I'm going to multiply this by 5. And so there's my answer. 5e to the x squared plus c. Differentiate this. Differentiate e to something, you get e to the same thing, 3 minus 2x. And then you have, there's a half here, but also you have to multiply by a differential of the bracket. So half times minus 2 is going to give you minus 1. And now it says integrate this. Well, I need to get rid of the minus, and I need to divide by 2. So I'm going to times both sides by a half, minus half, times by minus a half, times by minus a half. And so that gives me a half e to the 3 minus 2x gives me minus a quarter e to the 3 minus 2x plus c is my answer. There's my answer on the left hand side. These are 3 lines of working. That's how I want you to do it when you do the homework. I don't want you to abbreviate it yet because you're still learning. Okay, let's have a look. So let's rewrite this using indices. E to the power brackets 2 brackets 1 minus 2x to the power minus a half, close brackets. Okay, all my x's are inside a set of brackets, but that's inside another set of brackets. So it's a double application of the chain rule. So in that case, I must switch to first principles. So y equals e to the u equals 2 brackets 1 minus 2x to the minus a half. Differentiate this, dy by du equals e to the u. Differentiate this, du by dx. Du by dx equals, the 2 comes down, multiplies that, gives me minus 1, times the minus 2 gives me 2, 1 minus 2x to the minus 3 over 2. Multiply the 2 together, so that gives me 2, 1 minus 2x to the minus 3 over 2 times e to the u. What was u again? It was 2 over square root 1 minus 2x. So there's my answer. This differentiates to give me 2 over 1 minus 2x cubed and square rooted e to the 2 over square root 1 minus 2x. Okay. Differentiate this. Well, at first glance it looks as though you can't differentiate it because all your x's aren't inside a set of brackets, so you can't use the chain rule, but it's a fairly easy one to multiply out. E to the 2x plus, remember when you're multiplying you add the powers, e to the 3x. Now you differentiate that, gives you 2e to the 2x, and you differentiate that, it gives you 3e to the 3x. Can we differentiate when the base isn't e? No. So we're going to have to rewrite this when the base is e. Now I'm going to introduce you to my machine which leaves things the same. It's very expensive. I charge £350,000 for it, and if you put something in it, it comes out the same. It doesn't change the thing at all. So this is my machine. What it does is it learns whatever you put in, and then it does e to the power of that. So whatever you put in, whatever function you put into this machine, you'll get the same function out at the other side. Okay, it will be the same. And it's kind of obvious that that it leaves things the same, because learning and exponentiating are the inverse of each other, and if you do them one after the other, they'll cancel each other out. Of course, if you do something in between, they won't cancel each other out, but we don't. We go straight from the learn to the e to the power. So let's chuck this into our machine and see what it comes out as. Of course, we know it's going to come out as 2 to the x. It's going to come out unchanged. Let's chuck it in. Okay, so put it in there. Okay, we've got to learn it. Learn of 2 to the x. Well, we can use that property of logs, which is to bring that x down there. Okay, that's nice. And then we're going to do e to the power of all of that. So e to the power of x ln 2. And then it comes out the other side and it's the same. Oh, but it's not. It's e to the x ln 2. But they must be the same as each other. So what we've done is we've figured out how to rewrite 2 to the x so that the base is e. It will become e to the x ln 2. And just to make it clear, the ln 2 is just a number. It's roughly 0.693. So e to the 0.693x is what we have there. It's not very accurate, so there's no need to change it to 0.693. Better off leave it at ln 2, but I've done it now. So okay. We were still trying to differentiate it. We haven't differentiated it. So all we've done is we've rewritten it, and so now we're ready to differentiate it. So let's differentiate. Let's rub this out. Oh, such a nice machine, eh? But it's gone now. Been scrapped. Okay, so we're going to differentiate. Instead of differentiating 2 to the x, we're going to differentiate e to the 0.693x, which when you differentiate it gives you e to the 0.693x. But you've got to multiply by the differential of the brackets, which is 0.693. I'm fed up of writing these 0.693s. Why am I writing them? Oh, they were just ln 2s. Let's put them back again. Let's put that back as ln 2. Ln 2. Let's put that one back as ln 2. Be much neater. Ln 2. Okay, so there's our answer. But hold on a second. This is the same as this, is the same as this, is the same as this. I can just put that back now. Now that I've differentiated it, I can just put it back as 2 to the x. So put that back as 2 to the x. 2 to the x. So there's our differential of 2 to the x. So when you differentiate 2 to the x, it gives you ln 2 times 2 to the x. I'm sure you can guess the differential of 3 to the x now, and 5 to the x, and 10 to the x. Now they want me to integrate 2 to the x, so I'm just going to change my arrow to go the opposite way, and I'll be integrating. So arrow goes the opposite way, I'm integrating. So the integral of this, ln 2 times 2 to the x, would be this. But I need to get rid of the ln 2, I just want to integrate 2 to the x. So divide by ln 2, divide by ln 2. And so the answer is 2 to the x over ln 2 plus c. Differentiate this. You've got 2 sets of brackets there, and your x's are inside a set of brackets. No, this x is outside a set of brackets, so we can't use the chain rule here. But this is still easy to do. We can just rewrite it. We can rewrite it by splitting the numerator. So we can rewrite it by splitting the numerator. 1 over e to the x plus e to the 2x over e to the x, which gives you e to the minus x plus, when you're dividing you subtract the powers, e to the x. So all I've done is rewritten that, e to the minus x plus e to the x. Now differentiating it is going to be easy. Differentiating that, differentiate e to the x gives you minus e to the minus x, and differentiate e to the x, that just says e to the x plus e to the x is my answer. Differentiate this, so we've got 1 plus e to the 2x to the power 3. It's a double application of the chain rule. We should really revert to first principles just to be on the safe side. Don't want to risk getting it wrong. 1 plus e to the, oh sorry, I'm replacing the thing inside the big brackets with u. So everything inside the big brackets with u. So that gives me u cubed, u equals 1 plus e to the 2x. Differentiate this, dy by du equals 3u squared. Differentiate this, du by dx equals 2e to the 2x. Multiply them 2 together. It gives you 3 times 2, 6, e to the 2x times u squared. U was 1 plus e to the 2x, all squared. Overlaying the chain rule on a function of anything, any new function. What does that say? Any function, anything. That's probably a typo. Okay, so we now know the chain rule. So if I introduce you to a completely new differential that you've never come across before, so I've introduced you to this r cos x is going to differentiate to give you 1 over 1 minus x squared. You've got that rule now, and you can now differentiate anything that's like r cos x. You don't need to understand what r cos is. You don't need to care. So if I want to differentiate r cos x, well, you might think that if r cos x differentiates to give you 1 over 1 minus x squared, then r cos 5x would differentiate to give you 1 over 1 minus 5x squared. And you'd be 90% right, but you forgot to multiply by the differential of the brackets. You just need to put a 5 in there. Obviously that could be rewritten as 25x squared. If you differentiate this, you might think it's 1 over, I've replaced the x with 2x, 1 minus 2x all squared, but you've got to multiply by the differential of the brackets, which is 2. If you want to differentiate this, you might call it 2 over 1 minus root x, sorry, 1 over 1 minus root x squared, just replacing the x with root x, but you've got to multiply by the differential of x to the half, which is a half x to the minus a half, and that all needs tidying up. Okay, and the homework, So it's on the new website on mathschool.com, and the omit doesn't apply to any of you at all, so it's this homework here. Next week you're going to be tested on the chain rule, and here's your extension question, which is if you can get it right, then you get one of those get out homework free cards. But this is a peculiar question, so I do verify it by giving you a similar question to do in the lesson, just to check that